Today we're going to talk about creating graphs of polynomials. And we're going to be given some specific information about them, like the degree, the number of roots, and the leading coefficient. And the first thing that I see when I see a degree on there is I automatically translate that into turning points. How many turning points do we have? Because that can be something that can be helpful for us when we're drawing our picture. So we're going to sketch a polynomial with the given characteristics. If possible, we're going to try to find multiple ways to sketch. And sometimes we can, and sometimes we can't. Some of the polynomials cannot be drawn. If the given characteristics cannot create a polynomial, we're going to write not possible and describe why. Note, while all examples have two sets of axes provided, not all of them will have multiple ways to create. So as we take a look here at this first one, it says third degree. So when we think third degree, how many turning points do we have? One less turning point than degree. So we're going to have two turning points when we draw this. Secondly, it says negative coefficient, negative leading coefficient. That means when we finish drawing the graph to the far right of our picture, we're going to be going downward towards negative infinity, which you're looking right on your graph. That's going to determine the negative leading coefficient. And then we have one unique real root. So our roots are where the graph crosses the x-axis. So let's draw a picture with two turning points and crosses just once here. And after I draw the picture, I like to go back and I like to check. Do we have two turning points? Because that two turning points at least is going to indicate that we've got a third degree. We've got two turning points. Negative leading coefficient. Here's what I was just saying before. As we look to the right on our graph is going downward towards negative infinity. So that means negative leading coefficient. One unique real root. Here's our one unique real root where it crosses the x-axis. And something that I may or may not have specified this week is when we have an odd degree function. In this case, this one is a third degree polynomial. What happens is that our ends go in opposite directions. So the fact that we know that this is a negative leading coefficient means that the end is going to go towards negative infinity, so the other direction is going to go in the opposite. When they're even functions, they end in the same direction. So just something maybe that can help. But that's one way that we can draw the picture, but we could draw it another way as well, although I'm struggling all of a sudden with it. I drew the parent function of this one, which the parent function of a cube is this, but I don't really want to draw that. It does give us one real root. If you think about our previous notes, we've been talking about how we have a maximum number of turning points. So at most we can have two turning points, but we don't have to have any turning points. And in this case, this picture does satisfy the conditions here, even though we don't have two turning points. We do have a third degree polynomial. By the way, if I pull this up, the third degree polynomial looks like this. Is what I was trying to draw it. And what I did here, though, is I reflected it over the x-axis, so I can put a negative in here. And there's our third degree polynomial, where we end with the negative because we had to have a negative leading coefficient. Anyway, I hope that some of you drew a different picture than me. But there's two possible ways that we could draw a third degree polynomial with those other conditions. Number two, fourth degree polynomial. So as we think fourth degree, how many turning points do we have? We have three turning points. I'll do a little bit better with the drawing of my pictures. We have a positive leading coefficient on this one, which means that we're going to finish our picture. So to the far right of our picture, we're going to be going upward towards positive infinity. And then we're going to have two unique real roots. So we could draw something like this. Again, once we draw the picture, let's check our work here. We have 1, 2, 3 turning points. We do have a positive leading coefficient because as we look to the right in our picture, we're going upward. And then we have a root here and a root there. Two unique real roots. Not the only way to draw it. We could vary that just a little bit and it looks something like this. Still has 1, 2, 3 turning points. We have positive leading coefficient because as we look to the right on the graph, we're going upward towards positive infinity. And we have a unique root here and a unique root there. Nice thing is, your picture can be a little bit different from mine, and it still can be correct. Number 3, fifth degree polynomial, negative leading coefficient, so we need to finish with our graph going downward towards negative infinity. And we have two unique roots. As we think about this, how many turning points does a fifth degree function have? One turning point less than the degree. So we want to get 4 turning points in here. 2 unique roots. We're going to finish with the going towards negative infinity. So we have 1, 2, 3, 4. And let's check it here before we get going too far. It's a little funny over there to the right, but we have 1 turning point, 2 turning points, 3 turning points, 4 turning points. Remember that a turning point is where a graph changes direction from increasing to decreasing or vice versa. We do have a negative leading coefficient because our graph finishes going down towards negative infinity on the right. And then we have an intercept right here as well as there. Those intercepts are both roots of the function. It turns out that that's the only way that I could draw that picture. As I think about it, there might be another way, but that's the only way I could come up with it, I should say. There might be a second way, but right off the top of my head, I could not come up with it. Notice that this is an odd function because it's a 5th degree, and our picture ends, our end behaviors are going opposite directions. Odd, opposite. Even, it's going to be the same. Which leads us to the 4th example here. We've got a 4th degree, negative leading coefficient, 3 unique real roots. Negative means that we're going to finish going down towards negative infinity. And because it's an even function, they're both going to be going down towards negative infinity in terms of our end behavior. 4th degree means how many turning points? 3 turning points. I need to get 3 unique real roots. So as we take a look at this, I could draw a picture like this. Again, I always like to go back and check. 1 turning point, 2 turning points, 3 turning points. Negative leading coefficient. We are going downward. And then we've got a root here, a root there, and a root there. 3 unique real roots. So we're good there. We can draw an alternative picture. And again, that's the nice thing about these is different people can have similar but not the same pictures. We still have to have these characteristics, but they're not always going to be the same picture. You might have something like this. Again, we should always look, check, but we've got 1, 2, 3 turning points. We finished going towards negative infinity, and we have 1, 2, 3 unique roots. So if we look at problem number 5, 6th degree, positive leading coefficient, 0 unique real roots. Well, 6th degree, first of all, how many turning points are we going to have? 5 turning points. So we've got 5 turning points. Positive leading coefficient. We're going to end going upward, and because this is an even function, 6 is an even number, they're both going to be going towards, the end behaviors are both going towards positive infinity. 0 unique real roots means we're not going to cross the x-axis. We're going to get 1, 2, 3, 4, 5 turning points, and I still need to check. I think I'm good there in terms of my picture, but it's always helpful to check. And when we check, 1, 2, 3, 4, 5, 5th degree polynomial. We do not cross the x-axis, 0 real roots, and we do end by going in the upward direction towards positive infinity, which means that we do have a positive leading coefficient. That, again, is the only way that I know how to draw that picture. And I'm pretty sure I'm right on that one. I'm not so sure on problem number 3, but I'm pretty sure I'm right on that one. Problem number 6. 3rd degree, positive leading coefficient, 0 unique real roots. I want to go back to something that we looked at on the calculator on number 1 that I made way more complicated than I needed to. But if we look at, again, the parent function, if we look at y equals x cubed, it's the most basic of the cubic functions. It looks like this. And I'll even pull it over here into our screen for a moment. That's the most basic. That's the simplest that we can draw that picture. Well, yes, it's a 3rd degree polynomial. Yes, it has a positive leading coefficient because we're finishing towards positive infinity if we look right on the graph. But we have an x-intercept right there. We have a root. Again, this is the most basic of x cubed functions, cubic functions. We cannot draw a picture where we don't cross the x-axis, which means ultimately that this is really not possible. And the reason is that a cubic function has to cross the x-axis. In fact, an odd function will cross the x-axis at least once. So I'm going to say that. An odd degree function will cross the x-axis. And unfortunately, there is one exception to that, but almost always an odd function is going to cross. So we'll look at the odd function with the one exception here momentarily. But then we get to number 7. Probably my favorite one on the paper because it's a quadratic, 2nd degree polynomial, positive leading coefficient, 1 unique root. And the reason why it's one of my favorites is because we've spent so much time on these types of functions this year. A 2nd degree, how many turning points do we have? We have 1. We've got 1 turning point. Positive leading coefficient means that we're going to end going positive. And again, here's an even case. And even functions have end behavior of going in the same direction. So since we know it's even, they're both going to be going in that same direction. And we have 1 unique real root. But we're so used to our quadratics here, which is the name of our function. And I should have named some of the others. But there's our problem. We've got one turning point. We've got positive leading coefficient. At the right, we finish going upwards towards positive infinity, and we have one unique real root. That is the only way that we can draw that picture. And we should be fairly familiar with that one. As we finish, first degree, negative leading coefficient, 0 unique real roots. Well, first degree function is a linear function. We have 0 turning points on this one. This is linear. And what originally that I did is I drew it like this. And I don't know exactly what that equation of that line is, but it would be something like y equals -3. It's where does the graph cross the y-axis? So here's a place where we have an odd degree function that doesn't cross the x-axis. But the thing is, do we really have a leading coefficient on this one? And the thing is, there's no variable in this, so there's no negative leading coefficient. So what I said on this one ultimately is that I said this one was not possible, and it was because of no negative leading coefficient. There is no negative leading coefficient.